If you don't know about his GitHub, go check it out. It's on Pythonisa. Oh no, what's the GitHub? We'll post it, right?
Yeah.
We'll have that all posted. And this is sponsored by the good folks at Intel and OpenVino. So thank you to Intel and OpenVino for hosting this workshop. This is a series of workshops. I think we'll have another, after this one, another 6. And actually, we're going to start picking up the pace a little bit. So we'll actually be doing it every week, every Tuesday. Same time, same place. So hopefully we'll see you here, enjoying some pizza, some cool snacks and stuff like that. And we also actually have some swag. We're going to be giving out some swag today. We have some cool custom T-shirts to be giving out to some folks, some other prizes. So stay tuned for that. Quick intro about Hacker Dojo. As you know already, Hacker Dojo is a 501c3 nonprofit. We're a tech community. We're an incubator that doesn't take equity. We are a cool hacker space for those who like to ideate, create. We're for the tech-quisitive and those who love tech. It is started on the ethos of sharing and learning and leveling up. We're 24/7 space. We do take donations. We'll probably have somewhere in the links on how to donate to our 501c and support our nonprofit. That would help and go a long way to continue this mission and bringing awesome educational programming and workshops to the community. That being said, with that all entailed, and now you're fully downloaded on what's going on, I'm going to give it to Chepe to start the workshop.
Thank you. I'm already here. Hey, good night, everyone. Welcome. So, this is going to be our first topic. It's more of a preparation, things you need to know kind of thing for the rest, which are going to be more task-oriented. Each of the following 6 workshops will be working on a specific machine learning task. And but today it's all about the data preparation. Why do we need to do that? Why do we need to process our data sets? And also, what are the mechanics of model training? So we'll visit those topics. We will explore a couple of libraries that will make our lives easier for that. And by the end, we should be able to train and evaluate and explore the results of a simple image classification model using deep learning. So, before we start, this is what we're doing. We are talking about data preparation and preprocessing, data exploration and visualization, the Python toolset that will allow us to do that, what are the mechanics of model training and evaluation, overview of deep learning frameworks, specifically we're going to be working with TensorFlow and Keras, and training an image classification model. That's what we're going to be doing tonight. Hopefully, it's going to be a short session. But please, rules of the game, if you have questions at any time, just raise your hand and come near the microphone that Ishai will be setting up in a second, so that we see you, we know that you want to ask a question, and also the people on the live stream can hear what you're asking, in case I forget to repeat any question that you might have. So, let's start. Quick show of hands. Who in here, the audience, is already familiar with machine learning, deep learning, training models, etc.? Okay, a couple of you. Great, so this is going to be apparently one of the first experiences regarding these topics for most of you. So if I skip something, please ask me a question. If you don't know what I just said, what it means, if it looks like I think that you should know, but you don't, I am mistaken, and I should be explaining everything. So please, raise your hand, come to the microphone, ask me questions, and interrupt me, please. Okay. So Machine learning is all about data. It's all about, it's a different kind of programming where instead of telling the computer what to do, we will show it data as input, and we will show the machine what we want as a result, and the machine will learn how to do that, how to go from input to output. And hopefully, it will give us a correct prediction in that process. That process of showing data and correcting the machine is called training. And before we can start, we actually need to do some stuff with our data sets. For starters, we want to scale our data, we want to format our data, we want to clean up our data. And also, we want to look at the data. We want to represent the data in a fashion that will be easier for us as a human to spot anomalies, to spot outliers. Maybe we have a data set where most of my data is in a region, but a couple of points of data points are like completely outside and most likely represent errors in the process of gathering data, or not necessarily are very representative of what our full universe will be. So we want to spot those, we want to deal with those. Maybe we will just filter them out or correct them. Or maybe we will just find that our data is widely all over the place, right? Across a wide range. It's important that we pay attention to this process of preparing the data, because we want to do two things. We don't want a particular feature in our data to skew the results of our model. For example, we don't want, if we are looking at housing prices, for example, that's one of the examples that I'm going to show later. You don't want, in particular, for example, the number of rooms to be the only thing that dictates what the price of the house is going to be, right? You want for each and every feature to contribute what it should contribute to the model. So, what do we do? First, we're going to look at the data, and we're going to try to find duplicates. Duplicates because if we have a duplicate value, we are reinforcing a particular data point to the model, and that might skew our model to predict leaning towards that particular value. We also want to find missing values. Most of the time, if we're dealing with numerical data, we might find nulls or nan, not a number. And what happens when we have those kind of values in our data, in a data set, is that our training process will fail. It will throw errors. It will stop training. It will saturate, go to none, go to infinite, just misbehave. And we don't want that. Also, in case we're dealing with categorical data, for example, today we're training an image classification model where we are going to call what is in each of these images. Each of these classes or categories are represented by an integer number, but most likely we want to change the shape of our data, and we want to do that by, for example, encoding it in a one-hot encoding, which is one kind of encoding that I'll be showing later today. We also want to scale our features, and we want to normalize our features. And depending on what we're working on, most likely we will want to do some data augmentation. Data augmentation is a process where I take my training data, do random stuff to it, like rotating it, zooming in, zooming out, cropping groups of pixels out of the data, just making it more difficult, so that our model generalizes better. And by generalizing, what I mean is the model will be able to predict a correct value when I show it a new data point that it has never seen. That's the whole point. We don't want to show the examples that we have in our training set, because we all already know the results for those. What we want is to be able to show new data points to our machine learning model, and hopefully the machine learning model will let us know what we want to know. So, what is data normalization and scaling? Well, normalizing usually means scaling numerical data between 0 and 1. It's important that we scale our data in that region, because as we will see later, the training process involves taking gradients and adding numbers. And if we remain in that region between 0 and 1, our computing resolution, the resolution for our floating points is enough for our training to be more effective. We also don't want our numbers to be too small or too big. That's something that can happen and may happen when we're working with deep learning, but there are a series of techniques to deal with those things that we'll look at in the following sessions. Scaling also means taking our numerical data and making it so that the mean is 0 and the standard deviation is 1. So that means most of our data is going to live between -1 and 1, right? And by living there, we allow the algorithms to perform better. And I say numerical data, and we will be working with images, but images are also numerical data, right? Each pixel is represented by a set of 3 numbers, which are the 3 colors that we use to represent an image in a computer: red, green, and blue. And we will actually be scaling those from the integer numbers of a byte, which goes from 0 to 255, to be between 0 and 1, right? So we'll convert those from a uint 8 into a float between 0 and 1, okay? Why should I do it? First, as I mentioned before, we don't want any particular feature to overweight the rest of the features. For example, in our images, we don't want any particular color channel to be more important than the rest. We want all of them to live in the same kind of region. It will also help converge our model faster and with better results. And some models just require us to do that. For example, there's a clustering algorithm, k-nearest neighbors, that will require us to do that for it to actually work. Okay? Questions? Yes. Can you use the microphone? Okay. Yes.
Okay, so you are telling about normalization of data. If I want to normalize it my way, if I want some data dominate on others, can I do that? Is it right way to do it, or at the end, or how?
Yeah, I mean, this is obviously, I'm addressing the general case. If on your particular scenario you want to give more weight to something in particular, you might be able to do it, but be aware that that might lead to the result that you want, but not necessarily the correct result. Okay, so we always have to be careful with those kind of manipulations. But yeah, great question. Any other questions? No? Cool. So let's move on. We will also be talking about data visualization and exploration. Exploration just means look at your data, okay? You might look at it in an Excel file. You might look at it as plotted in a graph. You might look at it in any kind of representation that will provide you with also useful information so that you can make the decision to clean it up, to normalize it, to rescale it, maybe to find correlation between features, which is something that you not necessarily want. If two features are correlated, you're feeding the same information twice. And you will want to use visualization for that, okay? Mostly, visualization will allow you for two things. It will allow you to look at the distribution of your data. How does my data changes when a particular feature moves across the range? But it will also allow you to deal with outliers. You will find them easily. And it will also allow you to make sure that what you think your data is what it really is. For example, you might have a set of 10 different classes and a set of 10 different names. But how do you know if each name corresponds to the class that you think it corresponds? Maybe along the way it changed the order. I don't know. All of those things have happened to me in the past, and it's pretty painful when you've invested a lot of hours into training a model and then you find out that, yeah, it trained, but what the model learned doesn't really make sense because your data was wrong. So don't skip this step. It's very important, and you will find useful information. We will be looking at three main libraries, and this is not just for today, but throughout this series. And if you keep going on using Python for machine learning and data science, there's a very high probability that you will continue to use these libraries. Pandas, I like to think of it as an Excel file in Python. It allows us to work with data in tables, operate over its columns, or series, as Panda calls them. It will allow us to merge, operate over columns, transform our data. Even sometimes we need to convert from one Excel format to a different Excel format, and the easiest way to do that is just read that with Pandas, do stuff, and then save it to Excel. And it will also give us very useful information, like statistics about our data, or I don't know, important metrics. NumPy is a library that is basically the way to do math in Python. I am not aware of any other math library that's as complete as NumPy. It operates mostly on arrays and matrices. And any mathematical operation that you can think of will be implemented here. So it allows you to programmatically do math over your data in Python. TensorFlow uses it, PyTorch uses it. All the frameworks are built on top of NumPy as a core part of the library, just because as a programmer, it's super easy to interact with. Okay? And it's also fast, so that's good. And then Matplotlib is an interactive library to look at our data visually. What that means is if we have images, it will allow us to display the images in the screen, but it will also allow us to plot graphs and compare data. And so if Pandas is looking like, it's like an Excel file, Matplotlib will allow us to plot the data in those columns and look at it immediately and see how it changes. Okay, before we move on to model training, I am going to show the first example. Let me just find out how we do this. Okay, so data visualization. Before we move on to the example, we're going to do an example regarding data visualization and exploration. A couple of questions. Can you read the text? Yes? More? Is that better? Okay. Okay. Do you have any question about any questions about what I just said? Data visualization, scaling. All good? Great. So we're going to be looking at the Boston housing dataset. This dataset can be downloaded from Kaggle. And it was originally collected in 1978. It's a very simple dataset. It's used for a lot of machine learning courses, mostly for the regression part that allows us to predict, for example, housing prices, depending on the features of a particular house. We're going to be using the tools that I just mentioned. Pandas, here's a short description about what it is. And if you're interested in learning more about pandas, you can visit this link here, pandas.pydata.org/docs. And Matplotlib will allow us to create some beautiful plots so that we can look at our data. So let's do some Python. And quick show of hands. Who here is already familiar with Python? Who is not familiar with Python? Okay, so 50-50. So I'm going to be stopping every time I show a new Python word, like this, import. So we were talking about using libraries, and we were talking about using Python. It's important to know that Python is an interpreted language. That means it reads our code in text format, and then on the fly compiles it and runs it on a virtual machine. And while we're doing that, there's a set of features that belong to Python. There's a set of libraries that come with Python. Those are called the standard libraries. And then there are third-party libraries that we can use. So for those third-party libraries, you can use the Python package manager that's called pip. And you can search for packages in pypy.org, which is here. Okay? So for example, we will be using pandas. So if I look for pandas, we're going to see that pandas, I install it like this, pip install pandas. Now, I've already done this for you. I'm going to do pypi, yes, .org. Okay, and I'm gonna open this again here. And let me just do something really quick. Okay. So I don't know how to make this go away. But I want you to, if you have Docker installed, hmm? It's okay. No, yeah, I want to show this. So, okay. I'm sorry? It's PyPy. It's pypi.org. Yes, you can use. Yes. So, what this notebook is the TensorFlow notebook with PyPy and my matplotlib installed, and our data for the examples already copied into the Docker container. If you want to follow along on your computer, you may want to copy this and run that. It might take some time for it to download the image because being derived from TensorFlow is quite heavy. But apart from that, it should be simple enough. I suppose so. The notebooks are on the GitHub, yeah. I suppose Google Colab, you can upload the notebook itself, and yeah, you should be able to do that. And if not, okay, so yeah, if you need to install the packages, it's easy to do from within the notebook. So you just do pip install pandas, for example, and matplotlib. Yeah, in Google Colab, both of those should be already installed as well as TensorFlow. But in case you don't, this is how you would do it, right? So, once you have the packages available to your environment, now you want to use them. And to use them, you will use the code word import. So what import does is it reads the package, loads it into memory, and makes some stuff available. What stuff? Whatever the author of the package decided that's going to be the default that you will have readily available. Some packages are organized in a certain manner that you need to install, that you need to import specific modules from within the package. That is the case, for example, here. That's what's happening here. Import matplotlib, that's my package, .pyplot, that's my module, and then I'm saying as PLT. I'm just renaming it so that whenever I want to use it, I don't need to use like all this long name. I just say plt, plot, okay? So, as I said, pandas allows us to read data in several different formats. And that's going to be loaded into pandas calls a data frame. Now, what is a data frame? Again, think of a data frame like an Excel file on memory. And since we're reading the housing prices from a comma-separated values file, we can just see that it effectively looks like an Excel file. It has titles on the rows, and it has line numbers for each of the data. And I'm showing here, for example, I chose to display the first 5, okay? So it shows the first 5 rows here. And this data set shows me the average number of rooms, the lower economic status, PT radio, I apologize, I don't remember what this means. And this is the median value, okay? Description for this data set is available in this link that I provided here about the Boston housing prices. Again, I downloaded this directly from Kaggle, and it shows you some information about the data, the challenges related, all of that, okay? So we can do some stuff with our data frame. We can show the head, which will display the top part of it. We can show the tail. And these are like the last examples available in our data. We can also describe it, okay? So this will give us some interesting metrics, right? For example, how many rows do we have? We have 489 rows. That's all our data in this particular example. The mean of each column, the standard deviation for each column, the minimum value, the maximum value, and the top 25, top 50, and top 75% for each of these points in the data set. And then finally, we can also display our data in a plot mode. So for example, here I'm creating a scatter plot of the number of rooms and the median value. I'm assigning a particular label to each of those axes, and I'm showing it here. And you can tell that, as you might already have imagined, as the number of rooms increases, the value of the house increases as well. Okay? So in this particular case, if we want to build a model that will predict the value of a house given the other particular features, we can see that here we have a particular correlation, okay? Are directly correlated, those two columns. Okay, so if you want to learn more about pandas, I encourage you to visit the documentation. It's very well documented. It has a bunch of user guides that will guide you on what to do, how to do, what you can do with pandas. And even if you don't take a deep dive into it, it's worth it to spend an hour or two just looking at what it does. Because later down the road, you might want to do something with it. So just visit the user guide, look at the tutorials, look at the guides. It's super helpful. Same thing with Matplotlib. To be honest, I'm a very beginner user of Matplotlib. I use it as I just showed, but it does a ton of stuff. I've seen people do very interesting, interactive animations. Again, take a look at the documentation, very well documented. All of these libraries are open source and are for you to make your life easy. Questions? Yes? It's okay. Give me a second. Can you come here? Sorry.
So can this visualization, whatever, can you request any type of visualization, like a cluster map or something like that? And second, and after that, can it be embedded to front end to HTML?
So for the first one, I think you can look at the available plots in the documentation. I can tell you what I've used. I've used the scatter plot. I've used histograms. and I've also used it for displaying images. I don't know if there's any particular figure for clustering, but I suppose, yeah. Yes, so you can dynamically create the plot and export it as an image, and then load that image from the front end. That's how I would do it without knowing anything else about the thing. But yeah, I mean, I know you can use it to export the plots as images. Yes. Can you ask the question here on the microphone? Thank you.
Sorry to hear you answer this maybe at the previous session, but in general, for these Jupyter notebooks, you have it set up with Docker and whatnot. Is this also possible to run through like on AWS and SageMaker to follow along with the class?
I suppose so. I've never used it. The options that I offered on the previous session was either using Google Colab or Kaggle, which both are like free for a while. So yeah, and I mean anything that can run Python, and preferably that already has the machine learning libraries, frameworks pre-installed, will be better because those can take a long time to install. So something like Google Colab is actually great for this, or Kaggle. Yeah. No problem. Any other questions?
How does OpenVINO fit into this?
So OpenVINO will be used from the following sessions. OpenVINO allows us to run machine learning models and deep learning models after they've been trained on other architectures or a plethora of hardware devices. In particular, today we are focusing into the data exploration parts before diving into OpenVINO. All the following sessions will have explanation of a particular task, training a model for that, or loading a pre-trained model and fine-tuning it in case it's a larger model, and exporting that to run with OpenVINO. So that's how OpenVINO fits with this. This is more of a prerequisite session, if you will, for the following, because I want to focus in the tasks themselves and not necessarily what model training is and what to do. I don't know if I answered your question. Hopefully I did. Data frame. DF stands for data frame. Okay. Okay, so let's continue. So now we're gonna take a deep dive into, oops. Model training, okay? So what it is? What is that? So model training is the process of teaching a machine how to predict data based on showing it some data, as I just said. For that, we will basically we need three things. We need the model itself, which is a sequence of layers. Depending on the model, those neurons will be connected in different forms. We will use a loss function. So a loss function is the measure of how correct or how wrong is our model when it tries to do a prediction, and in what direction, okay? And then the optimizer will allow us to basically take those losses, look at the direction that the weights are moving, and use something called a learning rate, which is how big of a step each of the weights in our model should take in order for it so that the next prediction will be more correct than the current one. Was that clear? Kind of? Not really? Let me try again. An optimizer is an algorithm that will iteratively look at our training data, feed it into the model. I'm sorry, our training loop will feed the data into the model, and then the optimizer will look at how wrong our model was and in which direction, calculate the gradient for those, and update the weights in the model. So there are several optimizers available. One of the simplest ones is called gradient descent, which is something that I have shown here as an example, where it shows basically a two-dimensional data, and the first prediction it's up here. It just with our model is usually initialized with random weights, so the first prediction will most likely be very, very wrong. And so the loss function calculates the error there, and then the optimizer looks at how each of the neurons contributes to that prediction, and in reverse decides in which direction each particular neuron needs to be updated, calibrated, so that the next prediction, for example here, is closer to where we're going to go. In this case, we're going to go to the deepest point of the graph, right? That particular algorithm is gradient descent. It's like the simplest example that we have, and most likely we won't be using it when training a deep learning model. And basically, when we think machine learning, we want to think of it in two different times in our process. The first will be training the model, creating and training the model. And then the second one will be using the model for inference. When we use the model to predict values, it's a different process and most likely a different scenario and a different setup. That's what we will do during the training process. The training process is usually more involved. And in general, these 6 steps is what we need to do. We want to split our data. Why do we want to split our data? Well, we want to split our data between our training set, a set of examples that we're going to show the model so that it trains, and a test or validation set. And that's a reserved set of data that we will use to validate that our model is training correctly. Imagine our model is a kid at elementary school, and our kid is learning to add 2 numbers together. If that particular kid only studies a fixed set of additions, let's say 1 plus 2, 2 plus 5, and 3 plus 7, that's the only thing that the kid is going to learn. So when we show it a new operation, our kid will not know what to do. So in order to prevent that, we want to use a validation set that will allow us to know if the model is really learning the operation that we want it to learn, or it's learning the data set itself. That process of learning the data set itself, we're going to call it overfitting. And it means that our model didn't learn to perform the task that we're asking it to. the model learned the data set itself. In this case, maybe the kid only learned those 3 basic operations and will not know what to do when we show it new data. It will most likely predict a wrong result. Then we want to define the model architecture. This is highly dependent of the kind of task that we want to do. One of the simplest tasks that we will be looking at when thinking deep learning is classification, in particular image classification. We're going to be using convolutional network today. And then we want to compile our model. Compiling just means preparing that model that we already created and pairing it with a loss function and with an optimizer. Again, there are a lot of optimizers available. We're going to use an optimizer that is particularly friendly. That's called Adam. And that's what we're going to be doing today. Then we actually train the data, train the model with our training data. For that, we're going to call our training loop. Today, we're going to be using TensorFlow for no other particular reason. That it's what I use to write the examples. But know that from any framework, you can actually export your results and run them on OpenVINO after conversion. And that will allow you to perform inference of your model on any hardware, no matter what you use to train that particular model. Then we want to evaluate our model. And by that, we want to make sure, one, that our model is training or has already trained and is not learning anymore and is not overfitting. So we will do that here. And then we want to test our model, right? No matter what the data says, no matter what the plots look like, we want to actually feed new data and see that it does what we want it to do. So that was the last slide before we move on to the training example. Do you have any questions? Cool. Let's move on. Okay, so today we're going to be training an image classification model using a public data set that's called Cypher10. Okay? This data set contains 50,000 images for training and 10,000 images for validation. Each image is of size 32 by 32. And those are three channel images, means color images. So for this, we will import the necessary packages that we will be using today. Matplotlib, we're already familiar with that. NumPy, we're just going to use it once. I mentioned it before. It's super useful math library for Python. And we're going to be using TensorFlow, in particular TensorFlow through its Keras API. We're going to be building our model using the sequential API, which allows us to represent each of the layers as items inside a list. And then we're going to be using these 4 kinds of layers. Conv2D is a 2-dimensional convolutional filter. Max pooling 2D, it basically takes from a window the maximum number and reduces that window to that particular number. Okay. Flatten, it's basically a reshaping layer where we change the result of a previous layer into a single dimensional array. And then dense is the name that Keras gave to fully connected layer, which is just a layer of flat neurons, fully connected, all the inputs to all the neurons. Okay? So that's what dense is. I'm sorry? We were going to be training a convolutional model. The reason for that is when you do a fully connected layer, the traditional set of neurons, layer after layer after layer, you cannot actually build a model that's too deep. What will happen if you try is that the weights when you calculate the gradients will become very, very, very small, so the model will not train very effectively. There's a limit to that. So one of the techniques that one can use is, instead of using all the features connected to all the layers, to all the neurons, is you create filters that will allow the model to detect certain features in the images. What features? I cannot tell you a priori, but you can look at that a posteriori, and we will do that on the next session, where you'll see what it looks like on the intermediate layers. But basically, the first convolutional layer usually finds things like edges, shapes like circles, particular curves that might be representative to your data set, gradients, that kind of stuff. So a convolutional filter will show you. So you feed an image through a convolutional layer, and the result will be peaks where those patterns exist, okay? And then you do that again, and you will be able to combine those patterns together and find higher abstraction features. For example, if you have a very deep model, like ResNet 50, for example, 50 layers of residual convolutional networks. One of the last layers finds things like a wheel, I don't know, the front panel of a car, or a flower. Very complex patterns that are representative of what you will find in your data, and that will allow your last layer to let you know what that particular example is. Again, we'll do a deeper dive in those topics on the next session regarding classification. But for today, that's basically it. Now, these are just a few of the kinds of layers that you can use. There are several much more complicated layers than this. If you look at the Keras documentation, I think it's keras.io, go to the API docs, and then go to layers, you'll see that there are a lot of convolutional layers, pooling layers, recurrent layers, preprocessing layers, normalization layers, regularization layers, attention layers, reshaping, merging, a lot of different layers. So depending on the task, you know what layer you will be connecting from one to the other. Throughout this series of sessions, I will be telling you what layer does what in what particular task, and why it's important to use it like that, okay? For now, let's focus on the classification task. And again, we're going to be using the Cypher10 dataset. Cypher10 dataset is distributed on basically all the frameworks. It's also available to download from Kaggle. If you run this import statement first, and then this statement, you'll see that if you don't have it, it will just download it very, very fast, decompress it, and make it available to you in variables. Okay, so now, for those of you who are new to Python, we are calling a function that's deeply nested inside TensorFlow. TensorFlow Keras datasets Cypher10 load data. That's a function call. And we are loading the result into a tuple of 2 tuples, okay? So what happens is that this load data function returns, imagine an array with 2 big columns. Those are the training data and the test data. And each of those 2 columns is divided into 2 again. The X, which is going to be the input, and the Y, which is going to be our target, our result, the correct results. That's what's going to be what we call the ground truth, okay? And cool. And here I'm just making a copy from the Y test to the original test. I don't remember at this particular moment why I did that. And then Cypher 10, as I mentioned, are 60,000 images in total, 50 for training, 10 for testing. And all of these 60,000 images belong to one of those 10 classes. Yes?
I was going to say, wouldn't it be a good idea just to use 10% as your benchmark for your testing data or your training data?
And can you please repeat that on the microphone so that the people on the live stream can hear what you're asking? Sorry.
Okay. Yes. Wouldn't it be a good idea to use 10% of your testing data for training instead of 25%? Why did you use 25%?
We're using 25%. First, this split is already performed for us. Our data set is too small to use only 10% for validation. Depending on your model architecture, you might need a lot of data. And I'm going to be honest here. The hardest challenge that you will find when dealing with training machine learning, deep learning models in particular, is going to be to find enough data to train your model so that it generalizes well. This is a very small data set. 60,000 images sounds like a lot, but it's really not. Especially because we're not doing any kind of data augmentation or any fancy techniques to make it better. Usually you want to train your data with hundreds of thousands, if not millions of images, and then perform augmentation on top of that so that it generalizes better. So answering your question, why do we do a 25% split here? Just so that our test set is more representative of the distribution of our data, because our data set is small, okay? Cool. Then let's look at the data. We're gonna look at the first 25 images for the training set. I'm gonna make this smaller just so that it's easier to see what it is. So we have things like frogs, which are not very discernible here, trucks, deers, horses, sheep, cats. And then our validation data. You can see that the nature of the validation data is very similar. We have cats, planes, sheep, frogs. Same shape, same format. That's very important. We cannot train on one data and validate with another data that's distributed differently. You want to basically do a split of your data. And very importantly, once you've made your split, don't change it. Even if you retrain your model, change your augmentation techniques, modify your architecture, if you want your experiments to be valid, do not change your testing data. You need to be testing against the same set so that you know if your model is improving or if it's actually getting worse. Okay?
Can you just get the flexibility?
Yes. Okay. Okay. Hopefully that's visible again. Now, we're going to scale our model. This is the only NumPy operation that we will be performing here. So, what we're doing here, I'm gonna go back, so just so that I show you what it originally looked like. I'm gonna add a cell here, and I'm gonna do X train. I'm gonna show you the first example. First, you'll see if I call shape on this, you'll see that it's a 32 by 32 by 3 matrix. So that's a three-dimensional matrix of 32 by 32, or in other words, a three-color image of 32 by 32 pixels. What type is this, you might be asking? Well, I assumed it was a NumPy array, but if you call the function type, the built-in function type, on an object in Python, you'll get the type. So yeah, effectively, it's a NumPy in the array. And then, what does it look like? Well, in a Python notebook, if you call it just like that, you'll see that it is an array. If you pay attention here, it says array, and then open bracket, open bracket, open bracket. Why is that? Because it's a three-dimensional matrix. So we're going to have 32 by 32 numbers, and then a bracket closing, and then opening again for the next channel, and then opening again for the next channel. And that's how our data looks like. If you remember at the beginning of the session, I said that images are usually stored as 3 channels of uint8 integers. 8-bit integers. That means numbers between 0 and 255. And as you can see, that is the case here. You can also do, I think, max. And you can also do min. It's between 0 and 255. Okay? Even if when we display it, we don't find any of those numbers, because for brevity, the notebook doesn't throw everything at us, right? So that's what it looks like. Now, what does our Y look like? Well, it's a one-dimensional array with a number 6. And so the number 6 is 0, 1, 2, 3, 4, 5, 6. Frog. That means that our first image in our data set is a frog. Okay? So all these bunch of numbers that I was showing is this particular image. Okay? Questions? No? Cool. But after we scale it, if we look at the same example, you'll see that now we have a set of numbers that go between 0 and 1. That's all we did. We did that at the same time for train and test on the X side. It means on the input examples. We scaled all the numbers from a uint to an integer float between 0 and 1. Super simple stuff. This is allowed not by Python, but by NumPy. Okay? We are using the division operator here, but had this been a traditional list, Python list, this operation is just not possible. It is only possible because this object is a NumPy array. Okay? And as I mentioned before, we will use NumPy arrays to feed our data into the TensorFlow model that we'll be training. Okay? Now, before we look at the explanation of the model, let's look at how we create it. We're using a sequential, and we're going to do convolutional 2D, max pooling 2D. So basically what this does is it increases the number of dimensions, and then we reduce it again to the maximum activation. And we do that again and again. Only on the last time, instead of doing a max pooling, we do a flatten. We just reshape our results so that they are on a single dimensional array. We run that through a fully connected layer of 64 neurons with ReLU activation. So a ReLU activation is a rectified linear unit activation. So a linear unit activation, a linear unit function is a function that when x is 1, y is 1. When x is 2, y is 2. So it's a unitary line, linear function. And a rectified, what the rectified part means is that when x is below 0, the result is going to be 0. So basically, that activation looks like this. Okay, below 0 is flat at 0, and then after 0, it's monotonically increasing with a unitary slope. Okay, so here's a short explanation. Basically, what we are doing here is running 3 convolutional layers to detect features. First, very simple features, then more complex, then more complex. And then we're going to add a fully connected layer. These layers are usually very useful to combine the results of the different neurons, different regions of an image, different activations for different kind of patterns. And then these layers allow us to combine those together in a nonlinear way. And then finally, we have a dense layer, which is a fully connected layer with 10 neurons. Any idea why we have 10 neurons here? Because we have 10 classes. Okay? So each neuron represents one class, and the activation is called softmax, and that means that every time we do a prediction, the output of these 10 neurons will add up to 1, because the output of each neuron is the probability of our input belonging to that particular class. Again, we feed an image, run it through all these layers, and then by the end, we will get an array of 10 different numbers. If we add together those 10 different numbers, we will get exactly 1. And the highest activation, the largest number in that 10-number array, is our predicted class, which hopefully will be very different to the other 9. Okay? Cool. Now, we're going to compile the model. If you're interested on the optimizer, here's a short explanation about the ARAM optimizer and the loss function that we're using, which is a categorical cross entropy. Categorical cross entropy basically is a loss function that we can use when we have categorical data, where each class is represented by an integer number. In this case, each class is first class is 0, 1, 2, 3, 4, 5. There are other ways of representing classes, which we will look at in a minute. And then we'll be using TensorBoard, which is part of TensorFlow that allows us to look at the data as it is trained, to look at our training process. It can also, it also has some features to explore our data set and maybe operate over it and do some stuff. I'm not going to go into that. Just know that it's much more powerful that I'm going to be showing you here. And we're going to be using that by setting up this callback. So a callback is a function that will be called after each epoch is finished. Now, what is an epoch? An epoch is what we call every time we feed all of our training data to the model. So we will feed it through batches, like little by little, little by little, little by little, until we are out of data. And then we say, we just ran an epoch. When that happens, we will be calling this function that does magic for us, saving in a logs directory, this directory here, which is this directory here, which doesn't exist anymore, well, doesn't exist now because I haven't run the example, but it will put some numeric data representing the results of our training there. Going back a little bit, we can explore our model here, for example, if we say, oops, summary. If we call the function summary on our model, we can see what is the shape of each of our layers. So once our model is already instantiated, we can look, we can see that the first layer has 896 parameters to be trained. This one has almost 18,500, 37,000, 65,000, and then in the end, only 650 for the last layer. In total, our model is 122,570 weights to be trained. That means this number of values will be updated each time we feed a batch of data into the model. Okay? Questions before we start the training? Yes?
That third value that was non-trainable parameters, what makes a parameter non-trainable?
Good question. Depending on your particular architecture, you might have either some layers that include values that you cannot modify, or you can actually freeze layers, and then out of all your layers, you can say, like, I want to, let's say you load a pre-trained model, and then you want to freeze, you want to conserve the first few layers and just train the last few layers. So then you would have a set of non-trainable parameters in your model there as well. Does that make sense? Okay. So to train the model, we do this very simple function call. We call the function model.fit method fit on our object model, and we're going to pass x from our training set, y from our training set. We're going to feed our training set 10 times only for the sake of time. We're going to use our test split for validation, and we're going to call this callback to save checkpoints that we can look at while our model is training. Before we do that, we're going to go to this other tab, run a new terminal. First thing we want to do is run bash, because We're not savages here. And now we're going to run TensorBoard. By calling TensorBoard -- bind all -- log dir wait, I need to go to the correct folder. Yeah. TensorBoard bind all log. I don't know if it's log dir or logs dir. Logs. And now we have a different service running inside our container. I'm going to use this tab here to go to localhost. Yeah, and we see TensorBoard. Because we don't have any data in our logs folder, TensorBoard doesn't really know what to do. We're going to make it reload data automatically every 30 seconds. And then we're ready to start our training process. So once we start training, TensorFlow does some magic for us by iterating over our data, batching it and feeding it into the model. It's a very small model. 122K parameters is very, very, very small. And that's why it trains pretty fast. We can see that our loss is going down by the end of each epoch, and our accuracy is going up, which is what we want. So what does those two numbers mean? So the loss is basically the value that we get after calling our loss function, which is the categorical cross entropy loss function. Basically it tells us how wrong we are in average when we try to predict a class, okay? And it's, in average, that number. Doesn't really have a meaning. What's important is that it's going down. And then the accuracy means how correct each of our predictions is, okay? And when we're training a classification model, this is the number that we want to look at. Depending on the task, we might be wanting to look at a loss, at accuracy, or at a particular custom metrics that we design for optimizing this particular model. So it's done. And we go back to TensorBoard, and we will see a few things. First, if we go to the Scalars tab, you'll see that we have this plot that changes accuracy through each epoch. You can see that on orange, we have the training data, and on blue, we have the validation data. Our training data keeps improving. However, our validation data, it means how our model performs over our split, it actually stops improving after a while. What's happening here? Who can tell me? I already said it. Yes? It's overfitting. Yeah, it's already overfitting. Or it's starting to stop training. This would be like a good spot to stop training, maybe. I don't know. Let's see. You can also look at it on a different format, like evaluation accuracy versus each iteration. This is not over every epoch, but over every step. Every time we feed a batch of data, this is how our accuracy changes. you can see that there was a plateau here, and then came back to life. Okay? Yes?
So can you just explain the meaning of the word itself, training? Because it looks like validate, not validation. For training, what moment was? What task was? For training what? To do what?
So this is our model here that is training when we feed an image from this data set.
To pick the image, that image.
Image.
Where is the line of command itself? How to pick the image?
How to feed the image?
How to pick it?
Yeah, it's going to be down below. I'm not there yet. Yeah, but this is something that I want to go over before we move on. We have some important controls here. By default, it's applying a smoothing of 0.6, which to my taste is too much. I usually like to run on simple models a smoothing of 0 because I want to see what it's actually happening. Especially with these curves that are very, very straightforward, right? You can also zoom in, zoom out, and change to a logarithm scale. This will be useful when you train larger models because at first it will train a lot, and then it trains just a little. So if you want to look at the improvements, you might want to change the scale as the model progresses. On TensorBoard, you can also look at the actual computational graph. So if you're curious enough that you want to know what's happening to your data when you feed it to the model, you can look at this. I'm not going to go into that, just know that it exists. And then you can also look at how the distributions of your weights in each of your layers changes over time, okay? Here you can see if there's a particular layer that's misbehaving for some reason, not training or training too much. That might be an indication of a problem in your model architecture, in your data. It depends, right? And then, lastly, you can look at the distribution of the weights in your data for each of the models. Again, not very informative for this particular model. Just know that it is here. It's important, for example, that on the last layer, the distribution is pretty flat, which is what we want if we are training a classifier. We don't want any kind of skew to a particular class, okay? So that was the process of training a model. How do we know if our training works? Well, we perform an evaluation. Again, I'm using TensorFlow today, and the evaluation just means calling the function evaluate. It will feed all my testing data into it and give me the result. The test accuracy is 0.69, which is a little bit better than chance.
Does it mean 60% or
It means that 69% of the attempts are correct, which is But again, it's our first machine learning model. We're just learning, and we're more interested in the mechanics of training a model today, more than training a model with high accuracy. That's going to be next Tuesday. Okay? We're going to be training a classification model, kind of like a big brother of this. And I'm going to be showing some architectures and some history of what happened to neural networks like before the 2000s and after the 2000s, and why we're seeing a plethora of applications since then today. Yes? It's no. 0.69 just, it means that when I feed all the testing set, all my validation split into it, 69% are correctly predicted, and then almost 31% are not correctly predicted. We're only looking at the result here, just at the final category. And then if you want to see what I mean, is look at what we're doing here. We are selecting an image. You asked before, how do I select an image? Well, I'm going to my test set array and selecting the first image. Okay, remember, the first image is already displayed here, and it's a cat. Okay? Believe me, it's a cat. Yeah, and then we're going to reshape it, adding a single dimension in the front, just because the model expects to be fed a batch of images, not a single example, right? We feed it like pushing a set of examples at the same time. So if we only have one, we need to put that inside another array. And then we call the function predict. What does predict do? What does predict do? It runs inference. It basically feeds forward our input throughout all the layers and looks at the result. Now, the result, we're going to take the argmax, which is the index of the highest value, and then we're going to index the class names with that value. Okay, I'm going to do that step by step. So if we look at the predictions, we can see that the predictions are a set of number, most of them very, very small. See, this is an exponential number, an exponential format, scientific notation. And we can see that this is very small, very small, very small, very small, very small, not that small. This one's not that small, actually. Okay? This one's not that small. All the rest are very, very small. If we do, predictions max, we're going to see that one of the numbers is actually very, very close to 1. So our model is pretty sure that that is the neuron that says, hey, that image is mine, and it's index 0, 1, 2, 3, okay? That means that when we call predictions.argmax, argmax gives us the index of the highest value instead of the value, and it gives us 3. Now, if we use that number 3 to index class names, which is just an array of strings with the names of our classes, put that number 3 in there, we know it's a cat. Okay. 69% of the time, this is correct with our model. I'm sorry? What's the second? The second highest. Let's see. I think we can do this. No. I think out. No, where? I'm sorry, I don't remember how to.
Can you just list all of the predictions?
Yeah.
It'd just be interesting to see that kind of sorted by.
Yeah, let me do an histogram. Macro histogram. Yeah.
Identify, hey, it got this one wrong by thinking it's like a dog. And the second category would be cat. And she's just getting too far into the weeds.
Okay, let me. Um, I don't remember how to plot. Okay. So, no, I'm sorry. I don't remember how to do this. Maybe at the end we can look at it. But if we look at the, like just by looking at it, this looks like the second highest, might be. It is 0, 1, 2, 3, 4, 5. Last names, 5. It's a dog.
That's it. That's it.
Yeah. Okay, so I guess if you gave me that bunch of pixels, I might say it's a dog or a cat. I don't know. Okay. Questions?
Can you show the original picture? Or is yours
Yes. So, so this is the original picture.
No, that's the one where you average pixels.
On this one, I haven't done anything to it.
It's like, oh, so they're just really low resolution pictures?
Yeah, they're 32 by 32.
Oh, wow.
Yeah.
Is there any reason why you use such a small resolution?
Just so that it trains quickly and we can do a workshop.
Oh, I see. Less data.
Yeah, so in the real world, what do you want? Okay, it depends. That's the consultant answer. What's the right resolution? Well, it depends. It depends on where is your model running. Do you need it in real time? How many requests do you want to process at once? For example, if you want very high accuracy, you might train a model with an input of 4,000 by 4,000 pixels. That's usually enough. Although, if you're doing something like face recognition, that's not going to be enough if you're looking at a camera. Then, you might be wanting for something like very, very high resolution, 4K or whatever. Okay? If you want very fast results, maybe 32 by 32, that's enough for you to know, like, yes, this is a stop sign here. I don't know. And then maybe you do something heavier to process correctly the sign or whatever. If you're running your model in a mobile device or in an IoT device like a Raspberry Pi or an Intel Atom, I don't know if that exists. Not Atom, Newton. I don't know. You might want to run maybe something like a 128 by 128, which is going to give you, I don't know, maybe 50 frames per second. So you can do interesting stuff. It depends. Okay? There are models pre-trained available for you in many, many resolutions. And most of the time, you don't want to train the model from scratch. One, because I don't know you, but I do not have millions of images stored on my computer or my server, whereas the people who train this actually do. Second, that work is something that's being open sourced for you to leverage. And that means you can take a pre-trained model that has very valuable information on the first set of layers, and you just want to tweak the last few layers so that you use that intelligence for your own benefit in your particular use case. So we're going to look at how to do that in the following sessions as well. Okay?
In this example, with this picture, cat was looking for the kid, 69% of cats. Can you explain, just to be sure, what you mean by layer, what you mean, I'm mistaken, I call it parameter, but you call it class, maybe we mean the same. Can you, on this example, this picture, explain us what parameters or classes or whatever?
Yeah, so we have 10 classes. So again, this is the Cypher 10 dataset. Okay? That dataset is public. You can download it and look at it.
So on this picture, can you show us what exactly it is?
So this is the dataset. This is an example of the dataset. If you want to look at different images, for example, I'm looking at the.
I thought it kind of shows what is in the picture.
So for example, here's. Oops, what am I doing?
Where is object place in the picture and color?
Wait. Okay, so here's another set of images. Okay, we have 60,000 images like this. All of them are. We have pairs of images. Okay, a pair is on X, it's an image, and then on Y is the class that it belongs to. So, for example, this says like this is an airplane. This is a frog. This is a cat. This is a dog. What is the what? 10 classes.
10 classes.
So these are the 10 classes.
Okay.
Airplane,
By mistake, I called parameters.
automobile, bird, cat, deer, dog, frog, horse, sheep, and truck.
You identify them also by color, by shape, by...
So instead of me programmatically telling like, hey, if you have like a little red and a little blue and a little white, that's going to be a plane. And then if you also find like a green background and a lot of red, that's also going to be a plane. And then if you find another bunch of red, but with round stuff, that's not a plane, that's a car. It would be exhausting to program that. And guess what? In the end, it's going to be wrong. Instead of doing that, I'm showing my model some data. I'm telling it like, this example is a plane, this example is a cat, this example is a deer.
So you don't use any other parameter other than names?
Just the names.
Okay, that's why.
Just the names. So that's what I'm feeding. Again, when we call the fit function on our model, the fit method on our model, I'm feeding on X, those are the images. On Y are the classes that each image belongs to. Those are arrays. So that means that the first X corresponds to the first Y. The second X corresponds to the second Y, and so on. They are ordered. If I scramble them, then my data is going to be invalid. Okay? It needs to be fed in the correct order. And then I do that 10 times. Each of those times of feeding my whole data set to the model is called an epoch. Okay? By the end of each epoch, my model has seen all of the examples in the training split. Hmm? Yeah, it says like, you fed me all of this, and then it saves a data point and goes again and again and again. Personal experience. If you're training a custom architecture, big deep learning stuff, you're going to be training for, if you're lucky, a few hours. If your model is really big, you have custom loss functions, custom metrics. You might be training that for days or weeks. I've personally trained models for a couple of days. One of the models lasted 13 days. When you're after very high accuracy, very particular metrics that will allow your model to perform correctly, this is a long process. I'm just doing this very fast so that you understand the mechanics. But the next few sessions, we're most likely going to take pre-trained models that have been trained over a ton of images for long periods of time, and we're going to use that intelligence to tailor it for our application. Okay? Yes, yeah, most likely yes. You do it on a GPU most of the time. A GPU is a graphics card or a server that includes that same processor, but not necessarily for graphics, but for deep learning, right? Intel has an amazing new set of graphic cards that we're going to be showing off on the next few sessions. And we, you can run, depending on the model, you can run the model on a GPU for very, very fast performance, or if real time is not really a requirement, you can run the inference on CPU. You might not need special hardware to make predictions. Or you might want to use OpenVINO and have it available to be run on whatever device you have available. Okay? Mining crypto is a completely different thing, and I don't know anything about it. So you can do both. Personally, I have. There's our most valuable member of the dojo actually won an Intel NUC, just a small computer with a graphics card in it, and he's working on a model called standard diffusion. Can you explain what you have? In the next session. Yeah, so basically, it's what graphics card is in your NUC? Intel Arc number? 770? Uh, I think there is the set of notebooks on the training. You can access some hardware.
Yeah, you can subscribe to Intel Cloud and get access to some hardware, including
Yeah. So, yeah. Well, I think for the sake of time, this is going to be it for today. We're going to take it from here next Tuesday. We're going to be diving deeper in image classification. We're going to be also looking at what you usually need to do to your data to train when you have categorical data. Today, we didn't really do much to it. We're going to convert those models. Yes?
Are you going to use the same Docker container next time as the Docker container you used this time? Did you use the different Docker container this time than what you used last time?
It's going to be this one.
The same Docker container?
I might update it with new data, but if you already pulled this one,
People should pull it in advance.
yeah, because it takes a long time to download, right?
30 minutes to get.
I'm sorry for that.
Yeah. Oh no, it's just the free Wi-Fi is pretty slow, and so if you should post a message for people to.
There's an event Wi-Fi.
Yeah.
We can handle that. We can take that offline.
I-
Anything else for the folks online?
No, thank you for the folks online. Please reach out to me if you have any questions. I will be looking at your comments, correcting me of all the things that I said incorrectly during this session.
And does anyone have a comment or question for that everyone else can hear online? You could just come up to the mic. Anyone else?
Any more questions?
For people online too, because they're watching.
No more questions.
Okay.
Okay, well, thank you very much, online people.